Just a second. Okay, thank you, the organizer, for setting this up. This is I'll show just discuss two issues from the recent work with Igor, and we are obliged to put this disclaimer for the granting agency. Both themes that I'm going to address have been mentioned already in Caroline's talk. So thank you, Caroline. It will be it's very related. So given the audience, I use these many slides just to introduce notation. I will run very quickly over them. So we have a okay, it doesn't. Can you enable my clicker? Okay. Thank you. So we have a system of ODEs called a dynamical system. We have associated semi-group. Oops, again. Again, for the discrete system, we have the same. Even if you do dynamical system in the continuous time, if you do numerical simulations, you have some ODE solver. It is actually discrete dynamical system. So actually, at the end, it ends up being discrete. So why are we interested in identifying this operator? Because if we have some observable that we want to evaluate along a trajectory, basically it amounts to taking the power of the operator, applied to the observable, evaluated at the initial conditions. So it's very interesting. This means in terms of linear algebra, we have a Krylov sequence of this operator U applied to the observable F. Observables themselves can be physically measured quantities or obtained by simulations. And again, each time we actually have a sequence of powers of this operator applied to observable of interest. Now, in a data-driven setting, we collect data snapshot as a vector-valued observables column-wise. So the column index is the time index or the discrete time index. And again, basically, each column is a result of applying something linear to the previous one. So again, this is, I mentioned again, Krylov sequence in this sense. So the idea of DMD is basically to mimic this by simply splitting the data into the leading and the trailing part, and then trying to figure out some linear operator that will push X into Y. So this is DMD, basically. So this matrix A is obtained by regression, solving the least squares problem. However, DMD, it's very, people tend to express DMD as a pure regression, so they lose this connection with the operator, which is kind of trivializing the thing. So if you just think of this data, if we just transpose the data, so just read it in different ways, we can say, oh, we have a dictionary of functions that span some subspace, and we have those functions evaluated in a certain number of points. So now, if the goal is to somehow identify some spectral information of the operator U, the best we can do in reality is somehow to compress it onto the subspace, the span of the dictionary, and then find out, since this will be d-dimensional, so there will be a matrix representation of the operator. So it's a standard procedure. Basically, you apply it to the basis vector, represent the result in that basis. Since this subspace is no invariant, there is no reason to be, there will be residual. And basically what is done in DMD is somehow figure out these coefficients by killing the residual. Killing the residual means you minimize it in the ambient norm. Here we mimic that by least squares. And then basically this matrix of the coefficients A is basically, if you compare to the DMD setting, this matrix of the coefficient A is just A transpose. That's why Koopman matrix and the DMD are basically a transpose of each other. Now, in the next step is you do like a Rayleigh-Ritz extraction, which means for this compression, you compute the eigenvalues and eigenvectors, and then use these eigenvectors to lift these coefficients of this matrix, basically, and using the dictionary, you obtain approximate eigenfunctions of U. They're approximate in the sense that this residual of this U phi equals lambda phi is minimized over the data that we have. Beyond that, we cannot do anything. In these applications of this spectral decomposition, the goal is somehow to have some observable and then represent it in terms of eigenfunctions. And then this is the key for forecasting, because forecasting means pushing this in time in the future. This means applying the operator U. Since this is the eigenfunction, each step forward will pop up 1 power of lambda. So this is the idea. And what comes out that these coefficients in these Koopman-Schur decompositions are basically the vectors of Q minus transpose. And Q is the eigenvector matrix of U, and U is A transpose, so Q minus transpose are the eigenvectors of A. And that's why in DMD, basically, once we have some data snapshots, we identify A, we identify eigenvalues and eigenvectors, and then we use the eigenvectors to somehow decompose the snapshots using selection of these eigenvectors. There's the coefficients, and these are the powers of lambda. This is the Koopman-Schur or DMD decomposition. The Schmidt's DMD means that this approximation of the compression is done by using the SVD, POD basis, and then we all know what DMD does. What happens in the literature is that people using DMD, basically, once they compute the modes in DMD, they use all of them in the next step, decomposition, forecasting, and so on. Of course, that would make sense if we knew in advance that the subspace would be invariant, so we really get subset of the eigenvalues. Otherwise, they are not. And then from the numerical linear algebra, we know that we can test A times Z minus lambda Z, the residual. And what happens is that even in the data-driven setting, this residual is available. We can compute it. So with each pair lambda Z, we can compute the residual. And some of the residuals will be small, some of them will be big. And that makes the difference. I'll give you just one example. This is the data flow around the cylinder vorticity from the DMD book by Nathan Coates and Stephen Branton and co-authors. And some 90,000 times 151 is the data matrix. So these are the modes. Once you compute these Z's, the modes, some of them, once you plot them, they are beautiful. Some of them are just noise. Okay. Of course, visual inspection is not good part of scientific computing, so we need something else. So what we did is, let's try to analyze the snapshots in terms of those modes. So this is a least squares problem. For the alphas, the amplitudes. So basically, if you use all of them, all 151 modes, and represent Fs with this 151 coefficients alpha, so those alphas are the same for all snapshots, we get very decent reconstruction, almost the full machine precision. But if you look the contribution, the amplitudes of particular modes, out of all of them, we see that some of them are contributing a lot to the reconstruction, and some of them are relatively, actually, their contribution is minimal. And of course, we do not know in advance which is which. Which will, once we solve V-squares, we will see, okay? So in the sparsity promoting DMD by Mihailo Jovanovic and Peter Schmidt, they do the sparsity promoting DMD is basically you constrain these least squares approximations of the snapshot by sparsity. And you have like a black box optimizer with sparsity control that does something and gives you a sparse solution. But interesting things happens because if black box optimizer gives you some modes, you have no way to interpret them. You say optimizer gave me that. So it's not full story. So for the sake of experiment for those modes, we computed the residual. The residuals, remember, are available. We can compute them. So once we compute the residual, then we realize some of the modes have small residual. The other ones have big residual. And then to compare these two graphs more easily, we plot the blue curve and 1 over the red. 1 over the red means if you have a sharp peak up, it is small residual. And I see those graphs basically are translations of each other. It tells you, once you compute the residual, you know a priori that these modes actually will contribute best. And you can use only those to represent the data. And then you have a, since those give you to high accuracy eigenvalue eigenvector relationship. So you can really interpret them, okay, like a coherent states that move in the direction of the eigenvector. So in this example, I put the threshold 10 to the minus 6 to the residual. And out of 151, only 9 of them satisfy this constraint. Those are 4 complex conjugate pairs and eigenvalue 1, which is always there. So with 4 complex conjugate pairs, we try to represent the entire dynamics, all 151 snapshots. So the error is about 3%, only 9 modes, 4 complex conjugate pairs. For comparison, so let's say you can see those, left is original, the right is reconstruction. So basically to the eyeball metric, they are basically the same, 3% error. Then for the sake of experiment, take the other ones. Take the 113 modes, those with the residual above 10 to the minus 2. The best reconstruction error has relative error, again, 1. So 9 can do much more, much better than 113 of them, because those 9 are picked out that those that are really latent state that actually are behind all the dynamics. Just to show how this residual works, there's another example with the same data set, only the observable is the norm of the velocity. Again, those 2 graphs basically are the same. And moreover, since here you get 151 eigenvalues, with the 2 sets of observable, you get 2 different clouds of points. But if in each cloud you pick those with the residual, let's say here 10 to the minus 3 threshold, then those eigenvalues basically coincide, although you use different observables. So here is inner and outer circles are velocity, vorticity, and velocity. So basically this residual bound basically somehow picks the right ones. Again, here just a visual inspection with only 9 modes. You can compare. This is the original reconstructed. Fine details. If you really zoom in, they are well reconstructed. Although you use a really small portion of the modes. Now for the second part of my talk, the second issue, also Caroline mentioned it, I think on the 2nd or 3rd slide, is DMD matrices can be highly non-normal. So the operator can be non-normal, so not unitary, not Hermitian, not skew Hermitian, non-normal, which means the eigenfunctions are bad in a sense. And even if the operator is normal, its matrix compression might be highly non-normal. Okay, so I will now first very quickly run over the EDMD just to repeat the notation. So basically, again, we have somehow we pick some dictionary. We have 2 sets X and Y of data snapshots. We build the EDMD matrix. And again, there is a compression U sub n of the operator onto n-dimensional subspace. And then that matrix represents the operator on that subspace in this way. The Z are the coefficients of the vector in this basis, and UN times Z are the vector of the action of U onto that psi. And again, we do the same as in DMD setting. So there is the Rayleigh quotient, theoretically written as a pseudo-inverse. In practice, you would never use pseudo-inverse. So you do SVD, POD basis, then do Rayleigh quotient in this orthonormal basis. These formulas here are written a little bit more complicated, like at first unnecessarily complicated, but in this form, it's easy to transform them to use kernel trick if you have a kernels and so you can make everything more efficient. And again, as I said before, you have this matrix, you compute the Rayleigh quotient, then like in DMD of the Rayleigh quotients, you compute the eigenvectors, you lift them up. So these are B times Si are the eigenvectors of U sub n, and then you use those and the dictionary to lift back to the original Hilbert space to get eigenfunctions or approximate eigenfunctions. And then those approximate eigenfunctions, it looks like this. So these are the eigenvectors computed in DMD, lifted once, lifted second time. So these psi's are approximate eigenfunctions. In the sense, this approximation sign means that in this relationship, the residual has been minimized over the data that we have seen. So that's the best we can do. There are many other details, though. These eigenfunctions can be tabulated. There are formulas and so on if you want to evaluate it at some x. And then again, the representation of the snapshot that I mentioned before. Now, in these notations, we use this matrix of the eigenvectors that diagonalizes, and then this red is now the red flag, basically. That in this business, we use the eigenvector matrix and its inverse. Any software tool that I know, MATLAB, Python, R, Octave, LAPX, CalAPX, you just name it. If you say eigenvalues of a matrix, if it's n by n, it will return n eigenvalues and n eigenvectors. No warning, no whatsoever. So if you give 100 by 100 Jordan block to MATLAB and say eig, it will give you 100 eigenvectors. No complaint, no warning, no nothing. If you look those eigenvectors, there are 100 copies of one, because there's only one. So that's a problem. Even if there are n of them, then it can be really almost parallel. And then any small perturbation, subspace they span, it's just fluttering wildly. So basically, all those DMD reconstruction in some subspace given in a basis that's really, really ill-conditioned, you end up somewhere else, basically. So that's a tricky point. One example of high non-normality that's well known is Orr-Sommerfeld operator when you linearize a Navier-Stokes. So this is one. Just one small dimensional examples where first the pseudo spectrum is complicated. So some eigenvalues are much more sensitive than the other ones. But for the problematic eigenvalues, if you look the eigenvectors, so here the matrix, so these are the absolute values of the inner product of the eigenvectors. They are normalized to 1. So those are the cosines of the angle between vectors. So you see here, there are nearly 1, which means you have like 100 eigenvectors just pointing to the same direction. Of course, non-normality is an issue, and it appears everywhere. Even if the matrix is non-normal, its submatrices or Rayleigh quotients might be non-normal. So sometimes this is like a silent killer in numerics, like they say for high blood pressure, it's a silent killer in the populations. So that's high non-normality is something that sometimes you have a method that analytically, when you, I think there was a Lazar's talk, when you increase number of snapshots in your method, all of a sudden it's worse. Analytically, it should be better. But when you increase the dimension, everything, the condition numbers go up. Actually, so what was killed the method was just numerics, not the method itself. That's it. Very often it happens. Numerics, you don't know whether you say eig or something or pseudo inverse, what happens in that sense. So then often what we do when we need the eigenvalue or spectral information of a matrix that's a priori known to be perhaps possibly non-normal, we switch to the Schur form. The Schur form means you apply similarity to a matrix, but unitary. And that's constrained. So the result is T that is not diagonal, but upper triangular. Upper triangular with the eigenvalues on the diagonal. So A, Q, T, Q star, you can write it as A times Q equals Q times T. And then from this, you see that the first column of Q is the eigenvector with this eigenvalue. The first two columns span invariant subspace that corresponds to these two eigenvalues, and so on. So in that sense, we still have a spectral information, but not in terms of eigenvectors, but each time of an orthonormal basis of a spectral subspace of some eigenvectors or some eigenvalues. Of course, in Schur form algorithm, the eigenvalues will come in an order that depends on the algorithm. So this ordering is random for us. So there is notion of ordered Schur form, which means once you have a Schur form, you can reorder it to get any ordering on the diagonal. So let's say I like these two green guys. I want that information. I can reorder the Schur to put them northwest. Once you do that, they are northwest, then you just truncate this. So you get you can orthonormal basis for an invariant subspace that corresponds to the eigenvalues that you are interested in. So that's the idea. And then now the idea is if we switch from the diagonalization to the Schur form, we want to ensure that we have all the functionalities of EDMD as we but with this Schur form instead of using eigenfunctions. So this, of course, is technical work. It has many details. I have no time to go through the details here, but we can repeat the procedure from before. So compute, instead of computing the Ritz vectors, eigenvectors, compute the Schur vectors, and then just lift them back. So lifting back here means we are lifting, but we are not getting eigenvectors at that level that we are lifted to, but we are getting orthonormal bases for the subspaces that correspond to certain eigenvalues in that order. And then, so this is how it looks like. So we get new set of functions that basically correspond to the eigenfunctions before, but relationship that u times, so you apply this multiplication column-wise, you get something that's linear combinations of the corresponding leading functions. And then this relationship, if you truncate it at any I, you get the same. So you get basically xi1 to xi I goes 1 to r. They span a flag of subspaces, like a nested subspaces. And then at each level I, you get an invariant subspace that corresponds to informations of the eigenvalues 1 to I. And then, of course, if you go with details further, applying kernel trick if necessary, if you want to, like an analog of Koopman-Schur decomposition, express the data as linear combinations of these new functions instead of eigenfunctions, the Schur functions. It's more technical, but it's been done, so it's okay. So basically, after we've done that, for any observable of interest, we can represent it using these functions and some coefficients. This corresponds to KMD. But now, if I want to do forecasting with this observable, I apply U from the left, pushing one step into the future. Then, since this is like an invariant subspace, and because of this relationship, what will happen if I, for the sake of forecasting, if I keep applying U from the left, pushing this G into the future, what will happen is the powers of this triangular matrix T will keep popping up instead of the eigenvalues before. So that's the difference. But each time we keep things represented in an orthonormal basis. So that's a big difference. One numerical example, or a couple of numerical examples to show you how this. So this is a very complicated quasi two-dimensional Kolmogorov flow, some dielectric fluid between two plates. So just to show that the analysis basically predicts what will happen in the actual computation. So the black curve, so here's 1. So this is a little bit more than 1, like 10. The black curve is the machine precision times the condition number of the eigenvectors in DMD. So this is the black curve. The green is the measured computed reconstruction error in DMD using those functions. It basically behaves as dictated by the condition number. And then here's a level of 1. So here the error is bigger than 1. Here's a little bit smaller because the condition number is smaller. And this is done in a sliding window in time. So this is one window of width 70. Later on, window of width 100. Again, the black curve, machine precision times the condition number. The green curve, this is the level of 1. So the error is actually all the time above 1. So if I have a reconstruction with error 1, any prediction based on that, it's doomed to fail. So it's for forecasting, this is like a simplified forecasting without any features like dynamically. I was telling Alex I put my timer at 24 minutes to be kind to him. It doesn't want to let me go. Okay. So basically this is a finally. So this first example is forecasting. Actually, the time horizon is long, but this is a linearized or Sommerfeld. So the data there has been generated basically already after linearization. So this is basically x plus one is a times x, and then it's easy basically. You can predict as far as you want. Here the dielectric fluid and cylinder flow is it depends on the time instant. But as I said, this is not the best forecasting we have, because we do have forecasting that dynamically adapts the window width depending on the performance and so on. This is just you keep window grow. Of course, if some point dynamic changes for some reason, you must be losing the. But then at that moment you will just forget the history and start learning from beginning. And this is the paper in revisions. It should be hopefully accepted soon. So the details are there. And there's one remark on software. I think we are very, very far. Much needs to be done before we are ready to have a really robust, reliable software that can run on high performance exascale machines and so on. So we have some progress. So since last year, the DMD is in LIPAC, included in LIPAC. We have a Hermitian DMD, that's like a physically informed DMD. I already submitted to LIPAC, but it's not being included yet because they have to make a C version, wrappers, whatever. We have a QR compressed decompositions where everything runs much faster. There is a streaming version. Ella will be in the next talk talking about some details on not in Koopman-Schur but in DMD for. Streaming like online with fast updates. And we have, of course, in this part of, at least to me, it's not yet clear a full interpretation in terms of eigenspaces instead of eigenfunctions. That perhaps more intuition for concrete problem would help. And so many of things are now a work in progress. So I hope there will be some, or if some of you is interested in some of these problems, let us know. Thank you.